Today's experimental math seminar speaker is our very own Lucy Martinez, who will speak about a mirror step variant of gambler's ruin. As usual, please mute yourself unless you have something to say. Go ahead.
Hi, thank you, Dr. C, for introduction, and thank you everyone for being here today. I will be talking about a project that I worked on last year. First, I will be going over some background and history on the gambler's ruin problem, and shortly after that, we're going to be going over this new generalization of the gambler's ruin, which we're going to call a mirror step variant. And we're going to conclude with some results and future work. Feel free to ask me any questions at any point of the presentation, or unless it's a long question, maybe it could wait until the end. All right, so let's get started. Consider the following scenario where we have a gambler who starts with X dollars and plays the following game. At each gamble, the gambler will either win $1 with probability 1/2 or lose $1 with probability 1/2. So you can imagine that the gambler maybe is throwing a coin, and if it lands on heads, it wins $1, or if it lands on tails, it loses $1. The gambler will keep playing this game until either they ran out of money, so they reach $0, or they reach a goal of winning some N dollars. So this gambler will start with a goal in mind of wanting to win N dollars. Of course, the scenario is known as the gambler's ruin problem, which was first posed by Pascal in 1656 in a letter to Fermat. So some questions that were studied and answered then were the following. What is the expected duration of the game? In other words, if the gambler starts with X dollars, what is the expected number of steps of finishing the game, whether it ends with $0 or N dollars? And what is the probability of winning N dollars? And we'll go over each of those and the formulas that exist. So let's start with the expected duration of the game. Let's say that this function g of x is represents the expected number of steps that the gambler takes to exit the game. In other words, it ends with either N dollars or $0. Then this expected duration satisfies the following recurrence relation with the following initial conditions. Here, g of x, we can think of follows, or why this expression is true. If the gambler is currently has X dollars, then to get to X dollars, either it went from losing or winning $1 to get to X. So either it went from X minus 1 to X, or from X plus 1 to X. And we add 1 to the count because it takes 1 step to get to X from either of those 2 points. And the initial conditions are both 0. We have g sub 0 equals 0 because, of course, if the gambler has $0, then the game has ended. So there's no steps there. Or if it's currently at N dollars, then the game has also ended, and hence the expected number of steps is 0. The solution to this recurrence relation is x times n minus x, which is a pretty nice formula. It's kind of it's symmetric. Let's look now at the probability of the gambler exiting the game as a winner, or in other words, winning or leaving this game with N dollars. if it starts with X dollars. Similarly, like the expected duration, this probability satisfied the recurrence relation. And in this case, the only change is we don't add the +1, and the f of n here would be 1, because if since this is the probability that the gambler exits the game as a winner, then if the gambler is currently at $n, it has reached the goal of earning $n, and so the probability of winning the game is 1, versus if it starts with $0, then didn't reach the goal, so probability of winning is 0. Again, this recurrence relation has a solution of x over n. So this is the probability for given any n and x. You can just plug into the solution and find out the probability that the gambler exits the game as a winner. There was also the case where if the probabilities are not the same, and for example, if we say that P is a probability of winning $1 and Q, which equals to 1 minus P, is a probability of losing $1, we can write the recurrence relation and its initial conditions, and sure enough, we can get an expression for the formula for f of x. And the way that it actually was, the way that the formula came out with is you just need to rewrite f of x in terms of f of x and f of x minus 1, and then do some manipulation to get a sum. And then after that, the sum has the solution that we see here in the bottom. So this is just shortly what has been done in the past in the classical gambler's ruin problem. So now, as I said, since that was going to be a brief description of the history and background of the gambler's ruin, let's get into the problem that I would like to talk about today. So the gambler's ruin problem can be restated as follows. So instead of thinking of a gambler playing this game, we can think of random walks where we have a particle starting at a point x on a line segment of length n. And as long as this x is between 0 and n, then this particle can move to the left by 1 unit from x to x minus 1 with probability 1/2, or to the right from x to x plus 1, probability 1/2. So we think of it as this scenario, then we're going to adjust this classical case to the mirror variant. So let's add a third step, which we're going to call the mirror step, and hence the name. And adding a third step looks as follows. So we have the particle that is at a point x on a line segment of length n. And now the particle can move in one of 3 ways. It can move to x from x to x minus 1, or to x plus 1 as usual. But the third step that we are going to be calling the mirror step is moving from x to n minus x. And here we're going to have the probability Q1 is going to be the probability of moving from x to x minus 1. And then Q2 will be the probability of moving from x to x plus 1. And then finally, P is the probability of moving from x to n minus x. Of course, we have to ensure that all of those add up to 1. And more specifically, we're going to focus on one case for the rest of the talk. And so whenever I say symmetric case or mirror step, we're going to be referring to the case where Q1 and Q2 are both equal, and in particular equal to 1 minus P over 2. And throughout the talk, we'll see why we focus on this case. And at the end, we'll see what's still open. So again, I just want to emphasize that we will be staying with the symmetric case where the probability of moving to the left and then to the right by 1 unit is equal to 1 minus p over q. And p is the probability of moving from x to n minus x. Let's do first an example, and then we can get into the fun part. Let's say that p equal to 1 over 3. Then I'm just bringing back all of those points from the previous slides just to restate what that means in this scenario. And what that means is that the particle can now move from x to x minus 1, probability 1 over 3, from x to x plus 1, probability 1 over 3, and then from x to n minus x with probability 1 over 3. So all of them are the same. And let's say that n equals 5 and x equals 3. And let's look at what happens in the next round. Or in the next round, we have the following picture. Again, x is where the particle starts, and n is the length of the line segment. So if it's at x equal to 3, then I'm not sure if you can see my pointer. Maybe not. You can see it?
Yes,
Okay.
yes.
So if it's at x equal to 3, then it can move to the left with probability 1/3 by 1 unit, and then probability 1/3 to the right. And then this n minus x, which is 5 minus 3, happens to be at 2. So we have 2 arrows going to 2 here. So those are the steps that the particle can take at this point. So this is just like a picture to keep in mind throughout. Let's talk about the expected duration because turns out that studying the probability was harder than the expected duration of this scheme. So again, we're going to let g of x be the expected number of steps that a particle starting at x will eventually reach a position of 0 or n. And similarly to the classical gambler's ruin problem from the beginning, this also satisfies the recurrence, which is very similar. In this case, we're just replacing the half here and then the p over there and the g of n minus x. And let's look at an example of using this recurrence and see what we get. In this case, let's fix p to be equal to 1/2 and not 1/3 like in the previous example. And this is what the recurrence looks like. Now, of course, like in the classical gambler's ruin, we can set up system of equations and solve for the unknowns here for the x's between 0 and n, so whatever n is. But let's compute some examples by varying n, and these examples were computed using Maple, which is a computer algebra system. If you're not familiar with Maple, but I believe everybody here is. So this is just a table of some of the values for g of x in this example for p equal to 1/2. And I went from 1 to 6 for n, and then for the x values, it'll be up to 5 because n equals to 6, x ranges between 0 and n. So of course, let's just read some values of this table just to remember what this means. So for example, at n equal to 1, of course, since the line segment is length 1, if you start 1, then the particle has reached in this case n equal to 1. So there's no the expected duration of the game is 0. But for n equals 2, for example, x could be 1, since that's the only value between 0 and 2 integer value. And the expected duration here is 2. I don't know if you remember, but from a few slides ago, the expected duration formula for the classical game was x over n. So maybe we'll see in the next slide if we can tie these values back to the classical game. So again, these are just some values for some n's, which were computed in Maple. So hopefully we can see both tables here, but the top table are the values for the classical Gambler's Ruin game, where we vary n between 1 and 6. And then the bottom one is the mirror step variant that I've been talking about for the past few minutes, where we also vary n between 1 and 6, but when p equal to 1/2, p being the probability of the mirror step. So this example was kind of not too bad, because we can see that the values on the table in the bottom are just multiples of 2 of the table on the top. So of course I did pick an easy p to be 1/2, but we can kind of see, or we can observe that there is a relationship between the expected duration of the classical game and the mirror step variant. And sure enough, this multiple of 2, it so happens that we can think of it as maybe it's the reciprocal of the p value that we start with, because the reciprocal of p is 2. And turns out that that's almost correct. The formula for the expected duration of ending at 0 or n in the mirror step variant, where we are focused on the symmetric case, is just the following formula, which is, again, we see that x times n minus x, but we have to multiply by 1 over 1 minus p. So in our previous example, because p was 1/2, it was maybe a little bit misleading, but it is related back to the classical Gambler's Ruin games. And the nice thing about this is that when you plug in p equal to 0, you do recover that x times n minus x, which we're not going to see for the probability formula. So in this case, again, if you plug in p equal to 0, you're going to recover the formula for the expected duration of the classical Gambler's Ruin. So this one was not too bad, but we'll see why the probability was not as nice as this, as the expected duration, in a minute. Okay, so what about the probability? We want to find out what is the probability that our particle starting at x will eventually reach n in the symmetric case. We're going to define this quantity f of n raised to, it's not raised to p, but what this means is that this f of x is going to depend on n, p, and x. And f of x is going to be the probability that a particle starts at x and will eventually reach n. And just like before, this probability satisfies the following recurrence relation. Now you might, or maybe a suggestion to solving or to coming up with a closed formula for f of x would be to try to use some recurrence relation tools to figure out a closed formula from this expression and its initial conditions. But we can see that this n minus x here will make this a little bit difficult. Okay, so let's just look at an example. We're going to do the same thing that we did with the probability. We're going to compute some examples and show a table of what some of these probabilities look like. And for this case, again, we're gonna look at p equal to 1/2. Again, we're just gonna look when n is between 1 and 6, greater than 1 and 6. And so these are some of the probability values. And we can stare and stare at this data for a while. And at least for me, staring at this data didn't help with coming up with the closed formula. But I do gotta say that, for example, the first column, the numerators, those numerators were in the OEIS, but I believe there was no formula for those, or maybe there was. I can't remember now. I did look this morning and I already forgot. And also I believe the denominators of the first column are also there. But one observation that we can see here is that we can't really quite find a nice relationship as we can't really find a nice relationship between n, x, and p. And so let's bring back a table with the probabilities of the classical Gambler's Ruin game and just look at it for a minute. So on the top, again, we have a table for the probability of ending on n starting at x for the classical game. And then in the bottom, we have the symmetric case for when p equal to 1/2. Again, you can stare at these numbers and try to see if there's any relationship with the numbers on the top and the bottom. At least I couldn't find one. If you can, let me know. But yeah, so this is, I just wanted to show you that looking at the top table and the bottom table wasn't good enough. Okay. So let's talk about the experiments that went on for this task of trying to find a closed formula. So instead of trying to guess a formula for fixed p, because in the previous slide we were fixing p and varying n, and then moving along the rows for x, we are going to be fixing n large enough, fix x, so your starting point, and vary the p-values. So let's state what we're saying here more formally. So we're gonna try to guess the following limit. What we want is to find an expression for the limit as n goes to infinity of this quantity here. Again, this was the probability of ending at n if the particle starts at x with some fixed p. So this is the quantity we're interested in. We're not interested in the exact value. We're interested in the limit as n goes to infinity. So maybe this numbers converge to some number is what I'm trying to say. Or this as n goes to infinity, maybe these values will converge to something. So let's look at an example. This data that I'm going to show next for the next few slides was also gathered in Maple using some procedures. We're gonna let n equal to 100, and we'll see why 100 was good enough to you. We're gonna let x be equal to 1 and set p to be 1 over k for k be in the set of 2, 3, 4 up to 9. So the way that this quantity of n raised to the p of x, again, this is not a power. The way that this was computed is fixing n and x, and then you set a system of equations, and then you only are interested in when x equal to 1 to get these numbers. Maple was pretty fast computing this data, even though it was n equal to 100, which you can imagine that it's 100 different, or not in 100, 99 different equations from the recurrence, and then with the initial conditions, you go back and solve for each of those, and then we're only interested in x equal to 1, so we only extract that information. And those numbers in the table below are the probabilities that we get when we fix n equal to 100, x equals 1, and for different p-values. Here, these numbers, some of them you can recognize, like 1/4 is all the way in the bottom, and then 1/3 over here. So maybe you are already seeing where I'm going with this, but what we're trying to see is if this converges to something. And we said, or I said earlier, that n equal to 100 was large enough in the sense that if you were to, instead of say n equal to 150, then you should, using Maple, you should get the same or around the same values as we have in this table. So what we discovered soon enough was that these values were in fact converging rapidly to some.
Excuse me, Lucy, can I see the square root of 2 at p equals a half? Is there a square root? I was just, well, square root, it looks like the square root of 2 minus 1. Is that?
Yeah, that's what's coming next.
Thank you.
Yes. All right. So what I was going to say next is that thankfully in Maple we have a function called identify, which is based in part on the continued fraction expansion of any given numerical value. So we're going to use that function on our data, and just like Dr. Broadhurst suggested, that should be square root of 2 minus 1, the top value. And this is what we get when we use this function identify in Maple for each of those numerical values. So again, n equal to 100 was good enough because no matter if you increase n, they'll still converge to these values. So that was pretty nice. We still haven't proven anything yet. We're still doing experiments, which is why we're in this talk, experimental math. So we'll eventually build up to how we came up with the expression for this. Anyway, so yeah, so these are the values, and for some of them we can see exactly what it is. So for example, this is just 1 less than 4, the denominators. Or if you think of it as 2 squared, then that 2, and then you add 1 here, similarly here. So let's explicitly state what this suggests. Again, that suggests that the probability of the particle starting at x equal to 1 and ending at 100 converges to some number. And the first guess for when we start at x equal to 1 for this limit expression was that this should be equal to this expression on the right hand side, which is square root of p minus p over 1 minus p. Again, we're gonna call it guess because we haven't proven anything and we're just doing experiments. But this will be proven later. In fact, doing the same procedure, we were able to make also the following guesses. So if instead of starting at x equal to 1, it starts all the way on the other end, minus 1 unit, so n minus 1, then this is the expression for that limit. And so let's just bring back from the previous slide with the expression from starting at x equal to 1. So we're kind of going inwards. And I'm not sure, I guess I would have to give you more than a second to stare at it, but maybe we can kind of guess what could happen next. But let's just look at x equal to 2, and then maybe we can start throwing in some suggestions of where this is going. Okay, so for the next guess, using Maple, the particle starts at x equals 2. This was the expression. And so far here, we still see that 1 minus p factor in the numerator, but this one is square. And we do see still square root of p at the top. But so far, there's no way of telling how from x equal to 1 to x equal to 2, how those expressions are related. And this is also the next guess for x equal to n minus 2. Again, we start at x equal to n minus 2, and we're interested in the probability of ending at n. And this is also the expression for this limit at the bottom. So I guess I should say that Maple was pretty good at computing examples and data for this 4 different cases. But if we were to do x equal to 3, we needed to get a little bit more clever, because we needed to increase the digits to try to use identify, because computer some data and then using identify on that data doesn't actually mean that we'll actually get some rational number in some of the cases, or some expression of each of them. So we needed to increase the number of digits in Maple in order to get the data that we needed. Okay, so because
Can I just make a quick comment? This second parenthesis in the numerator, it's obviously root p minus 1, right? Square. I guess you can combine it with the square downstairs.
Right, yes. Yes, so I should also clarify too that the way that I was coming up with this formulas were looking at the data after using identify, and then trying to find in OIS hopefully a formula for specific values, because as you saw in the data, we had square root of 2 minus 1. So what I would do is put in the data for any number that was under square root in OIS, hope for a formula, and then do the same thing with the other ones on like the numerator. Like that's how I was coming up with these formulas. But here's the way that we're gonna change things up to actually come up with the formula. You can check that the sum of the numerators of both these quantities equals p minus 1 square. So when you add both numerators, it should be p minus 1 square, which is pretty nice, because that means that they will cancel with the bottom. So maybe we are seeing something. So what we're gonna do is we're gonna change things up. We're gonna do a change of variables, and then we'll see why we're gonna be doing this. Then we're gonna set p equal to some number equal to 1 over k squared for some positive integer k. And moreover, we're gonna think of p as some square rational number. So p equals n squared. So that when I change back to p, we can just set n equal to square root of p. That's where we're going. We're gonna put everything in terms of n. So going back to the data, we want to look at the square p values. So that was 104, 1 over 9, 1 over 16. And those look pretty nice, because again, p equal 1 over k squared. On the right-hand side, we have 1 over k plus 1. And that's why that was what was nice about this symmetric case. I should state that whenever we looked at the square p values, we got a rational number, and that was one of the nice things of looking at the symmetric case. So again, we could conjecture that this limit expression is equal to 1 over k plus 1. But we have to remember that k is 1 over square root of p, or think of p as equal to n squared. And the reason why we're looking at p equal to n squared is because I want to get expressions in terms of n that look nicer than what the expression actually is. So again, plugging in here n equal to square root of p, we should get back to the expression from a few slides before you just have to multiply.
You should say in the table, these are approximations, right?
Yeah.
Yeah. You should mention in the table the right approximations, they're not exact values. It's
right.
It's a conjectured limit as n goes to infinity, and it's very close when n is 100, but it's not exactly, of course. Thank you.
Yes, I did forget to put the limit there. Thank you. Again, you might be wondering why do all of that. Well, if we were to convert all of those expressions in terms of n the way that I said to be n equal to square root of p, then we get this nice expressions in terms of n. And this was the moment of, oh my God, what just happened? Because we can now see that across the rows, if you add both expressions, they equal to 1. And so this was one of the observations to come up with an identity to try to find a closed formula for f of x, which is a probability of ending at n starting at x. But more importantly, the first observation that I was able to make was that on the left-hand side, we see odd powers of the binomial expansion of n plus 1's to some power. And then on the right-hand side, we see the even powers. And then on the numerator, and then on the denominator, it's just n plus 1 raised to x in this case. So all in all, let's turn a little bit to the binomial theorem. This is the binomial theorem statement. And we can take the odd or even part of this sum. It did make, usually it's 1 plus x raised to the n power, but I wanted it in terms of k. And so if we take the odd or even part, they both have closed forms, and the even part is just a plus instead of a minus, but this is the odd part. The reason why we need this is because, again, back in the slide, we were looking at odd powers and then even powers. And so we had like 2 cases, but we'll see that really was 1 at the end. So we were interested in what we are going to be interested is in the following sum. So it's not quite like the one in the middle. It's shifted by 2i in the bottom, or the exponent, I mean. But this is really what we want. And let's look at an example of why we want this. Say that you plug in k equal to 3 and x equal to n to the above sum, then you get exactly one of the values in the table to the left for the odd powers. So using this sum, this should help us get an expression to the values on the left, and then we'll do the same thing to the values on the right from previous slides. Again, this sum over here has a closed form, and this one was for the odd part, and then for the even part, it also has a closed form. It turns out that both closed forms were equal to each other, so we didn't really need to worry about the odd or even part, but we didn't know that prior to actually doing it. Okay. So since that expression in the top had a closed form, this is the closed form of after you go back to the variables of p when we said that n was equal to square root of p. So all in all, this limit expression is what we have on the right-hand side, which is kind of neat. Again, we have not proven this. This is actually a corollary in the paper because what ends up happening is that we actually find what the closed form is for the part inside of the limit. And then we take n equal to infinity, and then magic happens and we get the closed form. But what I wanted to emphasize is that we kind of went backwards instead. Okay. Was there another part? Oh, yes. We did give one observation about how they're adding to 1. So that's that lemma here, where only for the symmetric case, this identity holds where you add f of x plus f of n minus x. That should be 1. This is again only for the symmetric case when p equal, not p, when the probability of going from x to x plus 1 or to x minus 1 is equal to 1 minus p over 2, where p is the probability of going from x to n minus. So just a sketch of the proof, and the proof here, I discussed with Stein because he was interested in proving this identity, not algebraically, because in the paper it is proven algebraically, but Stein asked me, is there a combinatorial way of thinking about it? And so if you consider, instead of this expression that we have on top, we write f of x equal to 1 minus f of n minus x. So this is what we want to prove. So we want to find an interpretation for the left-hand side and the right-hand side. The left-hand side, f of x, is the probability of ending at n starting at x, and then f of n minus x is the probability of ending at n starting at n minus x. So if you were to do 1 minus f, this quantity in the bottom, that's the probability of not ending at n, which means that it's the probability of ending at 0 when you start at n minus x. Because of the way that these random walks are, in the sense that the probability of going to the left and right is the same by 1 unit, and the distance between x and n is n minus x, and then n minus x is n0 is n minus x as well. Then this quantities, again, we're kind of like hand waving this proof because it's just a sketch. This random walk should be equivalent. So this is like one way to think about why this identity holds. But again, in the paper, it's proven algebraically. Okay, because of that identity, it was crucial to have that identity, because without that identity, the closed formula for f of x wouldn't exist. Maybe, I don't know. We could rewrite the recurrence relation that satisfies the symmetric case to this recurrence relation on this slide. And this one, we can definitely find a formula for f of x, because now we have a linear recurrence and we have a bunch of tools to figure out what f of x is in closed form, because we also have those initial conditions. All in all, I'm not going to show you. Maybe if you're really interested, I'll show it at the end, because it is after the thank you slide, the formula for f of x, because it actually takes the whole slide to show it. But some future work, I forgot to fix this slide, so forgive me, but for the probability, both the probability and the expected duration, it is still open to give formulas for general Q1, Q2, and P, because again, we did focus on Q1 equal to Q2 being 1 minus P over 2. And I do have one conjecture to show where instead of fixing Q1 and Q2 to be the same, let me just show it off. If the probability of going from x to x minus 1 is the same as our probability from x to n minus x. This is the expression for the limits of if the particle starts at x equal to 1, take n to go to infinity. This is what it converges to. Again, this is a conjecture. It hasn't been proven. Now you can see that it does get a little bit more involved than the one where x plus 1 and x minus 1 had the same probabilities. But yes, so I would like to thank my advisor, Dr. C, for introducing this problem, and the NSF for funding this research. If you would like to read more about the paper, it is on my website, or you can scan this QR code. I will be posting the slides there too if you're really interested, and I will try to fix the one typo I had at the end. Thank you.
Thank you. Thank you, Lucy, for such a lucid and engaging talk. Any questions to Lucy?
Yes, please. Where does the square root come from? What's the quadratic ambiguity in your problem?
Yeah, that's a good question. I don't think I have thought about it that much, but I guess I'll show you this. This is an expression for f of x. So it turns out that when you take n to infinity, this is why, because there's a bunch of square roots here. But I don't think I have thought about it in terms of the problem itself. But thank you for your question.
Well, let me put it another way. Was your discovery of the square root completely empirical, or did you have some idea before these numerical investigations that the square root of p might appear?
Oh, no, I had no idea prior to
So
this.
it was a surprise to you,
Yes.
as it was to me.
Yes.
I mean, I saw that table. I saw 0.41412, and I recognized the square root of 2 minus 1, but I had no expectation that there'd be any square roots in your talk.
Yeah, me too. I didn't expect either prior to all those experiments.
Thank you.
Yeah, it was completely numerical using the maple identifier, and the square root of 2 was completely empirical. Then Lucy noticed the symmetry that f of n minus x plus f of x is 1. And in hindsight, it was not only true for the limit, but for an arbitrary one. And once you have this hindsight, it was possible to get this hairy formula by standard techniques. And then in hindsight, it turned out to be provable rigorously. But what was nice about Lucy's talk, she discovered the process of discovery. And without it, I think.
Yes, thank you.
More questions to Lucy? Well, thank you so much for coming, and the recording and slides will be available soon on the webpage of this seminar. Thank you. Bye-bye.
Thank you.
Thank you.